All right, so welcome to today's colloquium. We're delighted to have Deng. He'll speak to us about Hilbert's sixth problem, derivation of the Boltzmann and fluid equations.
Okay, so this is a joint work with Zaher, Hani, and Xiao from University of Michigan. Okay, so since they are mentioning this word Hilbert sixth problem in the title, so I think I will start this talk by discussing, introducing what is Hilbert sixth problem and the scope of our work. Okay, so the Hilbert sixth problem, in the beginning, Hilbert's original lecture has this huge title called Mathematical Treatment of Axioms of Physics. So if you interpret it in this most general and broad way, it could very much contain everything in modern mathematical physics, which has developed to the has gone kind of far beyond what Hilbert could imagine at this time. So if you interpret in this way, so there is essentially no, not even possible to say that something like this has been answered. Okay, so however, in Hilbert's original lecture, what he actually had in mind was this specific problem, at that time, which essentially corresponds to the, rigorous validation of the Boltzmann kinetic theory, which was developed kind of about 20, 30 years before Hilbert's lecture. I'm quoting, his in Hilbert's own words that the problem is about developing mathematically the limiting process there merely indicated, which leads from the atomistic view to laws of motion of continuum. So here, the atomistic view basically corresponds to the particle system of interacting particles that we're going to introduce, and the laws of motion of continua usually refer to the these fluid equations, the fluid dynamics, and the word there here means the work of Boltzmann on the principles of mechanics, which is essentially the kinetic. Okay, so in this sense, in his original lecture, he was pointing to this specific problem, which kind of made this clear proposal where we go from the atomistic interacting particle system to the laws of motion continuum, namely the fluid equations, via this Boltzmann kinetic theory as an intermediate step. Of course, let me remark that nowadays we know there are also alternative, other approaches where we go from the particle system to the fluid equations without going through the Boltzmann equation as an intermediate step. But this is another story. So we'll get to that, when we discuss the Boltzmann-Grad scaling. Okay, so this is the scope of this work I'm going to describe in this lecture, which is to complete Hilbert's original program proposed in this lecture and the corresponding article. Okay. So by the way, so there was in Hilbert's original article, he also mentioned, apart from this, he also mentioned another problem, which was to give the rigorous foundation of the theory of probability, which was kind of also related to this problem of kinetic theory. But that question, of course, has been answered, possibly in the 1930s to 40s. And this one that I'm talking about is the main, subject of this talk. Okay, so let's discuss what is this the details of this program. So basically, in the beginning, we have this particle system. Think of the atoms kind of interacting with each other, and we'll consider the most simplified model, which is the so-called Hart sphere model. We think the atoms are just Hart spheres; they collide with each other when they touch each other. And of course, in general, there is interaction potentials, and the Hart sphere case can be viewed as a limiting case of the hardest limit of potentials. Okay, we assume we have this system of interacting particles. Okay, then at the mesoscopic level, which is intermediate level between the microscopic and the macroscopic, we have this Boltzmann equation. So how do we interpret this Boltzmann equation? Basically, it describes the density function. They basically describe the distribution of the position and velocities of particles. So let's say if you have this particles, we have xj, vj, which is the position and velocity. Okay, and then the Boltzmann equation concerns this f p x v. So t is the time, x is the position, v is velocity, and this quantity basically means the density function of a particle at a particular position x and particular velocity. Okay, so at any point xv there is a density function describing the distribution of these particles. Okay, so this is given by the Boltzmann equation. And finally, at the macroscopic level, we have the fluid equations. How to get the fluid equations? Essentially, the idea is that the Boltzmann equation has a tendency of converging to the equilibrium, and these equilibrium are essentially the Gaussian, the Maxwellian, which are Gaussian functions in the V vectors. Okay, so if we go to this Maxwellians, essentially F is there is a rho t to the let's say 3 over 2 in 3D, and then we have e to the minus 2t. Square. Okay, and this since you have a Gaussian, in the distribution of v, so there is a mean kind of velocity, which is the center of this Gaussian, which in the end will be the velocity field, which is a function of t and x. So u equals u tx, rho is the density, again a function of t and x, and the t is the temperature. Okay, and these will satisfy the fluid equations. So of course it's a very rough description, but this is essentially the physical picture, and there is this two-step process. And this side will take infinity, and this side will take this step. This side will take this hydrodynamic. Okay, this is the picture, and then so this is a more precise description. We have these 3 regimes, and there are 2 limits. The first one is referred to as the Hani limit. We'll describe in detail. Essentially, it corresponds to the degree of freedom, the number of interacting particles going to infinity. The second is the hydrodynamic limit, which we'll see interpreted as this mean free path going to 0. Okay, so these are the 2 steps of the picture. Let me just say that second step is now much better understood than the first step. So we list in a number of references. So Cavendish, which was the first to derive the equation for the Euler limit as Euler equation as a limit, and this next work, the Marcy, Esposito, Lebowitz derived the Navier-Stokes, and then this work of Gauss and Saint-Riemann, which extended this derivation of Navier-Stokes, to the case of weak solutions. And there are, many, much more recent works that essentially answer this question, in various settings. But let's say in the most typical setting, we'll have the incompressible Euler equations, compressible Navier-Stokes equations, let's say in the RD or in the torus, this has been answered. Okay. So here, to complete this full program, the main difficulty comes from the first limit, the Hani limit, and we'll see in the process that this main difficulty actually comes from, how we will be able to connect the first limit to the second limit, and this requires the derivation of Boltzmann equation for arbitrary long terms. Okay. So let me get more precise about this Hani limit. So n here is the number of particles. So they have the position xj and velocity vj. Okay, so n is going to infinity in the limit. And we assume these particles are kind of diameter epsilon balls. And we assume they are the so-called hard sphere. They only collide and do elastic collisions when they touch. And then the question is, determine the evolution of the statistical quantities of the system. In terms of, you can think of it as, measuring these observables, essentially the average of a certain functions of x and v, along over all the particles. Essentially, what describing the evolution of these statistical quantities in the limit where n goes to infinity and epsilon goes to 0. Okay, so think we have in this picture, which is taken from Wikipedia. So we have this unit size box, which is essentially the domain we're looking at. We can consider parallel domain all kind of, even in the whole space, we are putting a decay condition on the at near infinity. So essentially that's still restricted to a finite domain. Okay, so we have many kind of small balls, little balls of size epsilon, where the number of balls is n. Okay, so this is the hard sphere dynamics. It can be described by the following system. So x is a position, xi, fj as the positions of the centers of the balls. So if the distance between xi and fj is bigger than epsilon, that means, the the particles are not touching each other. So you have this x and xj, so distance is bigger than epsilon. They are going in, linearly, and when they touch each other, if x hat minus xj is equal to epsilon, then they are going to collide. Okay, and the collision rule is given by this very simple kind of elementary expression. Essentially, it means that if the collision is a kind of a grazing collision, which means the relative velocity is perpendicular to the connection of the center, then the velocity do not change. On the other hand, if the relative velocity is in the same direction as this center, so like you have this, then the velocities of the two particles just exchange. The velocity of A becomes velocity of B, the velocity of B becomes velocity A, and so on. This is a pretty simple, follows from undergraduate physics that we have this formula. Okay, so a picture is like this. So we start from the pre is the kind of the pre-collision of velocity, and the post is the post-collision of velocity, which is they are related by this formula we have in the. Okay, so there are some technical things we need to do to make sense of this definition. For example, when there are three particles colliding to each other like in the same time, like this, but this will have probability 0, and we don't care about that. And with the removing number of probability 0 events, we can define this particle system as a time reversal and volume preserving dynamical system. Okay, so this is the starting point where we have this number of particles n, which is going to infinity, the size of particles epsilon, which is going to 0, and they are interacting via this kind of seemingly simple rule. The problem is that this n is so huge that it's very hard to analyze the behavior of these of each individual kind of objects. Okay, so we turn to the statistical point of view. That is, we consider, you can think of it as we're considering the random data problems, of this Hausfield system. So this is kind of a dynamical system or ODE, and then we are considering kind of random initial data. And we'll make this assumption, which is called the molecular chaos assumption, that the initial states, here state means position x and velocity b, initial states of particles are independent. Okay, so are random and independent. Okay, so this is an assumption that was made in the initial kind of work of Boltzmann, and all these subsequent discussions have been based on this assumption. So it's interesting to consider if you don't put this assumption, then what would happen? But mathematically, there is pretty few results in that direction. So let's assume that we have this initial kind of chaos assumption. So let's say this randomness is specified this initial density function. Since we have independence, so the joint density function, or kind of the marginals, s-point marginals, will be the tensor product of the 1-point marginal, and 1-point marginal is just a function of x and v. That's called this the initial data. This will be the initial data of the Boltzmann. Okay, so we're assuming this so-called Boltzmann-Grad scaling law, where n times epsilon d minus 1 equals to alpha, which is a constant or kind of go to infinity very slowly. So let me make some comments about this scaling law. Okay, so this n in particular, this value of n times epsilon d minus 1. So this n times epsilon d minus 1. So this n times epsilon to d minus 1 to inverse is the so-called mean free path. And this basically means the distance, a particle travels for first collision. The average distance of a particle travels before the first collision. The reason is that if you think of a particle, it has size epsilon. If it travels a distance, L, okay, then in the space, the volume of this particle that this particle occupies is essentially epsilon to the d minus 1 times L, which is the volume. And then the expected number of particles, since the total number of particles is n, and let's say the whole our whole space as size 1, then the expanded number of particles is n times epsilon d minus 1 times L. And if we want this number to be 1, which means that there is only one other particle in its way, which means they will only collide once, like the time that the distance it travels before the first collision. If this is to be 1, then this is called mean free path, and L will be the n epsilon d minus 1 minus 1. Okay. So in this way, this Boltzmann-Grad scaling we're talking about essentially corresponds to assumption that the mean free path is a constant. It's 1 over alpha, or alpha is treated as a constant, or slowly goes to infinity means mean free path slowly goes to 0. Okay. So this corresponds to the case of so-called dilute gas, namely that if you think you have a unit box and you have these balls of size epsilon, then in general the most number you can fit the balls of size epsilon is epsilon to minus 3, like in 3D. Okay, but now you only have epsilon minus 2 if the dimension equals 3, which means you are having a kind of low density setting, like your number is much less than the maximum numbers you can fit. This is the case of dilute gas. Okay, so it was first observed by Grad in 1940s that this setting, this Boltzmann-Grad setting, well, we'll see that essentially alpha is either constant or kind of very slowly, goes to infinity. This is essentially the kind of the only regime where we expect the Boltzmann limit to be valid. Okay, so this was first observed by Grad, so this is called the Boltzmann-Grad. Of course, let me say it again that there are other regimes where n is not epsilon to minus 2, but epsilon minus 3, for example. Essentially, think of epsilon minus 2, Boltzmann-Grad corresponds to the case of a gas, and epsilon minus 3 corresponds to the case of liquid. So in that case, you still have the particle systems. You still expect to have the fluid equations, but you're not expecting to derive it, via the Boltzmann equation. You have to find some other kind of method, some other kind of approach to get to these fluid equations. This is not what we're going to talk about, and this is not like in Hilbert's original program, he was specifically calling for derivation, that goes through Boltzmann-Grad theory. But of course, we know now that there are other approaches. By the way, mathematically, this other approach has a pretty limited progress. So the only thing I know of is a work of three people. I mean, Ola, Verodan, and Xiao, which derives this, but under this assumption that you put randomness, you add in randomness every time you collide. But this is not the kind of real physical stuff. Anyway, so in this talk we'll be restricting to the case where we go through Boltzmann, in which we're restricting ourselves to the Boltzmann-Grad. Okay. Remember we have this molecular chaos assumption that initially the position and velocities of the particles are independent. So now, once we start having collisions, then this independence will immediately be broken, because if two particles initially they are independent, fine, but then they go in straight line, they remain independent. But if they start to collide, then the velocity of these two will become dependent of each other. So there is this fail of independence. However, there is this key prediction, which is mathematically is a highly non-trivial thing, that this independence should somehow be preserved in the limit. And of course, the sense in which this independence is preserved is extremely subtle, that kind of the deviation from independence is going to 0, but it has to have a certain size. Like it cannot be kind of going 0, let's say, too fast. Okay, it has to have a certain kind of leading term that tells you that this is exactly a deviation from independence. We'll get there. Okay, but for now, let's just take this rough picture. Think the independence is somehow preserved in limit. Then for a positive time, even if we don't have independence for fixed number of particles, this independence is restored kind of in the limit where the n goes to infinity. And this is usually referred to as propagation of chaos. Okay, so let's say we assume propagation of chaos. Then the question is how do we characterize the the statistical behavior of the system for positive times? And again, if you assume this independence, then for later times at time t, the s particle marginals independence so gives you the fs t x1 v1 x is vs is a product j from 1 to s f1 of t xj vj. You have this factorization. Okay, so let's assume this. If you assume this, then there is a classical physical argument that tells us this function should satisfy a Kn equation, which is called the Boltzmann equation, and this is given by this transport equation with the right hand side being a quadratic nonlinearity referred to as a collision integral. Okay, the idea is think of if there is no collision, then every particle is traveling linearly, then we just have transport right hand side is 0. Now we do have collisions, which means that if you think of particle here, the number of particles in this at this velocity v, so there are this gain term, which means that two other particles collide, okay, to produce this particle at the velocity v, and this is given by the positive term in the integral. And there is this loss term, which means that this particle at velocity v collides with something else to give another particle that moves away from velocity. And this gives the negative term on the right hand side of this integral. So I'll not talk about the details of the equation, and the solution theory is extremely complicated, so it's not very much well known in terms of global strong solutions. I'll not get to that. The main kind of topic in this talk is the derivation of this Boltzmann equation. Okay, so timeline. So I'll go briefly through the timeline. So starting with the work of Boltzmann and earlier Maxwell, who first wrote down this equation, and then the observation of Grad that I just mentioned. First formulated this kinetic limit and did the formal derivation using the BGKY hierarchy. And the first kind of mathematical milestone in this direction was due to Lanford in 1975, which achieved this derivation for a sufficiently small time. Okay, so here there are two important quantities. This value of alpha, which is inverse of the mean free path, or you think of the collision rate. So alpha equals n times epsilon d minus 1, and t is the time. Let's say small t. Okay, so what Lanford's theorem corresponds to is where alpha is 1. So Lanford, so alpha is 1 and t is much less than 1. Okay, and subsequently there is work of Illner and Poverenti, which obtained these long time extensions where t is as large as you want, but alpha is much less than 1. So Illner alpha much less than 1, t arbitrary. That's in the case of RD, which is okay. And subsequently, in the last 10 years, there has been a lot of activities in this field due to the work of Bohino, Gallagher, Saint-Raymond, Texier, Simonella, and all these the collaboration of all these peoples. They investigated a lot of problems, including this 2014 book where they actually revisited Lanford proof and made it made one point of its rigorous and attained explicit convergence rates. And there is a sequence of works since in the last 10 years concerning derivation of various linear models, linearized Boltzmann equation, and kind of the fluctuations around the Boltzmann equation for such a small time, and so on. So there are lots of works. I cannot describe them all, but let me just say there has been a lot of activity in this field in recent years. One thing is that all these previous results are restricted to either the short time, t less than 1, or the near vacuum, where alpha less than 1. Alpha is a kind of somehow a density, measuring the closeness to vacuum, and or various linear problems like linearized Boltzmann or kind of linearized Boltzmann with noise and so on. Okay, so the key thing is that remember Hilbert's initial program that contains these two steps. The first step, we go from the particle to Boltzmann. Second, we go from Boltzmann to fluid. The point is that the second step, going from Boltzmann to fluid, essentially requires alpha to go to infinity. Okay. Now, in the first step, from particle to Boltzmann, this limit, whatever we do, we must allow alpha to go to infinity. Okay. So in fact, the derivation, if you consider the Euler limit, that essentially corresponds to alpha goes to infinity and t is equal to 1. And if you consider Navier-Stokes, that essentially corresponds to alpha goes to infinity and t also goes to infinity kind of simultaneously. In any case, the thing is that we need alpha to go to infinity, or and/or t goes to infinity. Essentially, this is the question. So can we derive Boltzmann equation partial dynamics for arbitrarily long time as long as solution to Boltzmann equation exists? So what is the difference, between, alpha, let's say t less than 1 or kind of alpha less than 1 or kind of alpha bigger than 1? The thing is that we have alpha, let's say 1, t less than 1. This corresponds to the case where collisions are still rare. You're going to a time where the expected number of collisions is tiny. It's 1 over 100, which means that it's only among 100 particles you are going to have one collision. Okay. However, in this case where alpha goes to infinity, it's the case of regime of many collisions. Like in the time you're looking at, each particle is maybe having like 5,000 collisions. Okay, so this is the fundamental difference of these two setups, and we'll see mathematically what these correspond to in terms of the convergence of the kind of the power series equations. Okay, so this is the question. I will answer this question positively in our main theorem. Before we say our main theorem, let me mention that there is a completely parallel theory concerning the interaction of waves, where the colliding particle system is replaced by a nonlinear Schrödinger equation, which represents interacting waves, and the Boltzmann equation is replaced by something called the wave-Kane equation, which is essentially the same as Boltzmann equation, but with a slight, with a cubic nonlinearity instead of quadratic. And the limit, the Chiari limit, is again in one-to-one correspondence, and this is called the theory of wave turbulence. Actually, this was the main motivation for us to enter into this problem Boltzmann, is to test, the techniques we developed for the wave turbulence. And in fact, this was our previous result, in 2023, concerning the same result, long time justification of wave turbulence theory. And these two theorems turns out to be pretty similar in terms of framework and in terms of the techniques. Okay, so we're not talking about the wave theory, so I'll just leave it here. But it's just good to know that these two things are not only closely related, and analogous on the physical level, but also much analogous even on the mathematical level. Okay, so here's our theorem. So this was the first theorem we proved, joined with Hani and Ma, in August 2024. So consider the half-sphere system in any dimension, bigger than or equal to 2, and under this Boltzmann-Grad scaling. So here alpha is either constant, or we can allow it to slowly go to infinity as a kind of log of the number of particles. Therefore, any fixed s is also allowed to go to infinity, but let's not get to that. And any positive time where the solution to the Boltzmann equation exists. So see, this is not just restricted to small time, but for arbitrary times, as long as you have a solution. Then in the Chiari limit, we have this. So we have this equation justifies the two things at the same time. First, the propagation chaos, the joint density of s particles is approximately factorized in the sense of L1 norm, and then the one particle density is going to be given by the solution to the wave equation. Is going to be given by solution to the Boltzmann equation, and this conversion happens in L1, and the right hand side is actually explicit power rate here. So we have this minus this in L1 less than epsilon to the alpha for beta, beta is something like 1 over 10d. Okay, so this is our first theorem that achieves the derivation of Boltzmann for arbitrary long times. And second paper, based on the first paper, we're able actually to complete Hilbert's original program in the sense that we go from the particle system to the fluid equations via the Boltzmann, equation as an intermediate step. Well, in this in the torus setting in 2 and 3 dimensions. So there is a technical reason why we're restricting to torus case, which we're not going to. Why we're restricting to dimension 2 or 3, we're not going to talk about. But essentially, to get the fluid equation, let's say Euler equation, you start with this initial data. Essentially, this Maxwellian, local Maxwellian initial data. Then in the pseudo limit. So let me comment that this limit can be taken as iterated limit. You first fix alpha and let n goes infinity, and then let alpha goes infinity. Or you can think of it as, alpha equals something slowly going to infinity with n, like log n. But then in either case, you get this density given by the solution to compressor Euler equation, with this initial data, given essentially by a local Maxwellian corresponding to the solution to Euler equation. In this sense, we are completing Hilbert's original program that establish this limit. Let me emphasize again that our theorem covers the range which is kind of close to the Boltzmann-Grad. So n times epsilon d minus 1 equals alpha, and we are kind of covering this range close to Boltzmann-Grad in the sense that kind of allowing alpha to go to infinity, in this very slowly rate. Okay, and again, as I said, this is essentially the regime where we expect to see these 2-step limits, particle to Boltzmann and Boltzmann to fluid, being both steps. Okay, so before we get to the proof, there is a number of future problems. So first, we consider the case of potentials. Let me write down the case of potentials. Potentials correspond to so dt xj equals vj. dt vj is in minus 1 over epsilon sum k now equal to j. Grad v is the potential, epsilon xj xk, and this is the thing with potential v, and then basically you're considering this v here. If v is a compactly supported potential, then essentially the result is pretty much the same, as the proof is pretty much the same as the half-sphere case with a number of extra complications. But the case where the case of long-range interaction where v is not compactly supported, this would much likely require new ideas, and especially if v is a kind of inverse polynomial with limited decay. So let's say v is vx is x to the minus alpha. Essentially, alpha goes to infinity, recovers the half sphere. But then the case where you have a kind of finite alpha, if alpha is large or kind of not so large, then this is something that probably requires further study, and especially when decay is not enough, this would require kind of new ideas. And a similar scenario is the derivation of Landau equation, where here instead of you're having, if v doesn't decay so fast, and there are kind of many different particles interacting, there can be possibility that many different particles interacting, having non-trivial interactions at the same time. And this is, in the formulation of Landau equations, you are having this so-called Landau. You're having this 1 over square root of epsilon. You have a weaker interactions, but then the number of interactions is big, so n equals epsilon minus d. But this is a much, I believe this is probably a much harder problem than the Boltzmann, and as of now, there is no result even for small times. And finally, it is a pretty ambitious plan that if we can extend our theorem to allow for weak solutions. And if you have weak solutions occurring as limits of the particle system, then that's essentially says that you're kind of trying to pick up a unique physical weak solution of Boltzmann, which is kind of widely open at this time. Okay, I'm just listing a few problems that be open for investigation. Okay, so if I have 15 minutes, let's talk a little bit about the proof. So what is the main idea of the proof? So how do we go from short time to long time? So the reason why all the previous results have been restricted to short time is because the strategy is by doing an expansion, starting from time 0. Okay, so there are two expansions that we do. First is the expansion coming from the hard sphere dynamics, from the particle dynamics. So we can do the so-called cluster expansion, also do it via the so-called UChicago hierarchy. This is a kind of two essentially equivalent approaches. And then there is a second expansion, that is expansion coming from iterations of the Boltzmann equation. Okay, so essentially what we do here is that we have this one particle density. So F1 is a sum in, let's say, n of these terms. And this term is O of t to n. They are kind of iterated integrals, or kind of they behave like powers of the time, power series of time, and then the solution to the Boltzmann equation and again this guy is O of t to n, is the iteration of Boltzmann equation. The thing is that we're doing a pair term by term comparison between this and this. We're actually showing that there are so-called leading terms in the expansion of the one particle density. The leading terms, they converge term by term to the corresponding term in Boltzmann. Okay, and then there are these subleading terms in the first expansion that converge to 0. And if both expansions converge, we can do term by term analysis to prove that. Then we get F1 converge to the Boltzmann. So this is a very simple idea that works for all the previous results concerning the short time set. Now this naturally puts a restriction on the time of validity that they cannot exceed the rate of convergence of the second expansion, which is usually much smaller than the time of existence for the solution. So what happens if we want to extend the long times? First of all, we cannot do the Taylor expansion at time 0, so we divide the time interval into small subintervals. That's to say, we go from time 0 to time tau. Tau is small time, and to 2 tau, and all the way to this t equals L times tau, where L is a very large number, a very large constant, and go to this. Okay, so we are starting from 0. We start from data 0, and then go tau, and then go 2 tau, and then go to higher order. So basically, we can try to go from each kind of L minus 1 tau to this L tau. Okay, so let's say we look at this particular setting. Now, what's the problem here? The problem here is that initially we have independence. The states of particles are independent. But after these times at L minus 1 tau, the states of particles will no longer be independent. If they are not independent, then how can we still justify this propagation of chaos? Okay, so it turns out that there is two sides of the coin. So first is that at later times, going from 0 to a positive time, we're losing independence. And second, this loss of independence is precisely the reason we can get from the time reversible system of Newton dynamics to the time irreversible equation of Boltzmann. Okay, so let me explain that. So first, how do we measure lack of dependence, lack of independence? Okay, we're going to have measure these by so-called cumulants. So think, if they are independent, then we have complete factorization. The Fs should be the S particle density, should be the product of these one variable functions. But now it's a partial product. It has a partial product for J not equal to H, and for J equal to H, we're having a function of all the variable, which is not factorized. Okay, so think of it as this G as the factorized part, and this EH, which we call cumulants, are the kind of non-factorized parts. Okay? So then Fs is the S particle joint densities, G are the proximate solution to the Boltzmann equation. For all purposes, we can just think they are the solution to the Boltzmann equation. And these are the cumulants. These represents the, interdependence of the states of particles. Okay, then the question is how do we analyze this? Okay, the behavior is that these things, they are small in L1. They better be small in L1 in order for our theorem to be true. And they, vanish, okay, in L1, but they're not small L infinity. So this is the main kind of issue, in the whole business. Okay, so these EH, they behave like indicator functions. Think of this. Let's say if you think of the cumulant of two particles, how are two particles related to each other? And this particle, okay, so you have this particle, and let's say we have another particle here. Okay, how are they related to each other? They relate to each other essentially if they have a collision in the past. So this is the time we're looking at, and then this is 0. So at time t, the states of these two particles are dependent essentially when they have a collision kind of in the past, or they are kind of related by sequence of collisions. 1 collides with 2, 1 collides with 3, 3 collides with 4, 4 collides with 2. Okay, essentially, this is when these cumulants occur, when these two particles are not independent. So it turns out that this EH is the indicator function of two particles, or just whatever number of particles connected by collisions in the past. So this is an indicator function. So it's not small L infinity, but it's small L1 in the sense that the set of support has a small measure. Okay, and in fact, the set of support is precisely the important thing we're going to analyze in our proof. That this set of support memorize the whole collision history, because two things belong to this set if they have a collisions kind of in the past. Okay, so we expect these cumulants to be small in L1. So as I said, these sets have small measure. So one key thing is that we cannot prove it directly. We cannot prove it directly by induction, because we're going to do an induction argument, going from one layer to the next. Okay, but we cannot prove this L1 bound by induction precisely because of this time irreversibility. Okay, the reason is.
Could you just say what the letter capital H means?
H is a subset. So you see,
you're talking about every subset of the particles?
Yeah, so we have S particles in total, and H is arbitrary subset of these S particles.
So you're looking at the past history of some particular subset of the particles at a certain time.
Yes, those particles are kind of related to each other, while the other particles just one by one.
Just that set identifies a subset of the phase space.
Yes. But the actual thing, we'll see. Okay, so the reason why we cannot do this is because if we go even for 2 time layers, we go from 0 to tau and go from tau to 2 tau. So we're trying to go from tau to 2 tau. But then there has to be a way that I can distinguish from going tau to 2 tau and going from tau to 0. Because when going from tau to 2 tau and going from tau to 0, we should get different results. This is a Boltzmann solution at 0, this is Boltzmann solution at 2 tau. But if we kind of are not careful, because the dynamics going from tau to 2 tau and going from tau to 0 is time reversible. So this is essentially the same dynamics, but we are getting different result. The reason we're getting different result is because the distribution, the law, kind of these statistics at time tau distinguishes from going forward and going backward. And this means that whatever information we have for EH, they must be, be kind of anti-symmetric in time. They must not be symmetric. And these kind of L1 norm or any kind of LP norms, they will be symmetric in time, and then you'll not be able to propagate this because of this time irreversibility of Boltzmann. Okay, so in fact, what we need to do is that we need to keep track of the exact formulas for these cumulants. And you see, these cumulants are extremely complicated objects because even in one layer, we can have two particles being in a cumulant by direct collision. They can be related by kind of sequence of collisions. Okay, arbitrary sequence of collisions, and not to mention there are many layers, there are multiple layers, and the two particles they can collide here, they can be connected back here in arbitrary layers. Okay, so you can see that this whole EH, the expression of this EH is an extremely complicated thing that contains all the history in the multiple layers. However, it is absolutely necessary in our proof to keep track of the information of all these exact forms. And this is why this proof is so hard and it takes so many pages. Okay, and this allows us to this is a thing that allows us to distinguish between going forward and backwards and thus create this arrow. Okay, so I think I have only a few minutes left, so I'll try to get a quick description of the strategy. So we're going to see the exact expression, which will be sum over these CH. CH is essentially the collision histories. Think of a diagram like this. This collides with this, that collides with that, and then we collide, backwards in time and so on. So each of these diagram is called collision history, and we're also representing by something we call molecule M. Okay, so essentially, just think of, never mind the formula. It's just sum of over all the terms, over all the all these diagrams, all these molecules, and we have this IN object. It's a pretty long expression, but essentially it means a normalized version of the probability that all these collisions occur. Like these two things, they don't collide arbitrarily. They have to satisfy some assumptions to collide, and you have all these assumptions. And the probability that all these collisions occur are given by this IN expression. And then we're getting to this sum. The contribution to density is the sum of all these contributions or all these collision possibilities of collisions and in terms of these diagrams. And then it's not hard. Let me say it's actually not easy, but conceptually it's not hard to prove this thing by induction. And then the key strategy, key difficulty in the proof comes in how do we estimate. Okay, remember we want to estimate L1 norm of EH. How do you estimate L1 norm of these things? These things themselves are extremely complicated integrals associated with extremely complicated diagrams. Okay, so this is an example of what we call molecule M. So here the same color represents a trajectory of a particle. So here you can think you have 5 particles. You see here you have let's say if you go forward in time, you're having this red collides with green. Okay, collides and red goes this way. And then on the other hand, the blue collides with the pink, and then pink goes this way. And then after this, red collides with blue again. Okay, collides with blue, and red goes this way to collide with green again. And then green goes this, red goes this, and blue goes this to collide with this next one, this brown one, and goes this way. So you see you have these such collision histories in all layers, arbitrarily complicated collision history in all layers, and we need to estimate the corresponding contribution of this for every diagram called molecule. So this is the thing that requires a lot of combinatorics. So there is a truncation which we skip, and then I'll show you the formula. So this is a negative power of epsilon, which I said is a normalized probability, this normalization, and you have this integral essentially over all the possible, all the possible velocities and positions and the times of all the particles at all times. You see here, this is a velocity here because this particle is traveling linearly. This is traveling linearly. There is a velocity here. There is a v1. There is v2. There is a v3, and so on. Okay, so this huge integral is integrating all these, this should be subscript ZE, but then, this initial data, and this essentially corresponds to the delta function, the direct function dictating that we have these many collisions. If you have this V1, this V2, and this is velocity V3, and this velocity V4, then because we're having this collision, then this V1, V2, V3, V4 is going to have some relations, which is given by these delta functions.
Which is the delta function?
So I'm putting this big delta, which contains a product of direct functions. So, let me tell you, it's
capital delta.
Yeah, so capital delta is a delta of V1 minus V3 plus V4 minus this V3 minus V4 omega, something like this. This is, you should recognize this collision form. It's a delta function of this. Okay, so this is a big integral, and the question is how do you estimate? So I'll just, if I have less than 1 minute, I'll just show you the strategy is that we are dividing the big molecule and the big integral into smaller molecules. Remember, we have this arbitrarily big. Okay, so we have this, and then we have this, and we have this. You can imagine, like, it's arbitrarily big molecules. We're going to divide them into small molecule by operation called cutting. So let me skip this. We're dividing by operation called cutting. So basically, if we cut this along these two edges, we're going to replace this molecule by cut this molecule into two sub-molecules, M1, M2. But each of these edges is turned into what we call ends. So it has only one atom instead of two atoms. And this at M1 we're calling it something called free end, and M2 we're calling this fixed end. So these are combinatorial things, but it turns out that it's very naturally, very nicely correlated with the corresponding integral expressions that we're defining with this big, integral of delta functions. This correlates very nicely with the cutting operation in the sense that if we cut M into M1, M2, then the integral of M is less than integral M1 times integral M2. Okay, and with that, we're going to cut this M into a number of, what we call elementary molecules, which only contains 1 point or 2 points. And then there is this two specific case of elementary molecules. The first one contains 1 point, the second one contains 2 points. Somehow, the first one corresponds to a particle colliding once, the second one corresponds to a particle collides twice. And the point is that the probability that particle collides once, the particle collides twice is strictly smaller than the probability that the particle collides once. Okay? And so basically we show that this thing, we kind of do not gain, do not lose. We get normal estimate for the corresponding integral, and for this right hand side, we get an extra gain for the corresponding integral. So these are elementary integrals. And finally, we'll show there exists an algorithm, a cutting algorithm, such that we can perform a sequence of cuttings, a suitable sequence of cuttings to the whole molecule that cuts it into molecules like left and molecules in the right, such that the number of molecules in the right is bigger than what we want. Okay, so I think essentially we need to have many good components, the good components on right, and this is the task of the algorithm. The algorithm is a purely, combinatorial object that I don't think I'll have time to talk about. So essentially, there is a procedure. Basically, the first procedure.
Good, but they're small. You want to put most of the junk into what you're calling good.
So the good is okay. You see
Confusing me.
Okay, let me explain. So the thing is to prove. Remember, we need to prove that EH vanishes. Okay, so EH vanishes means we need to prove that its IN vanishes.
So good means small?
Good means small, yeah.
Yeah, that's all I want you to do.
Okay. So there is this so-called layer selection process that if we have many layers, then we can always you have whatever, collisions you have inside, we can always find two layers, locate two layers, such that if we only consider these two layers, we are going to have, the enough number of good, good configurations. Then we can ignore all the other layers. So this allows us to reduce the multi-layer case, let's say there are 100 layers, to these two-layer case. Okay, so these are just rough, strategies, which we have no time to get into details. And then in the two-layer case, there is a key dichotomy, which consists of the number of components of the certain sets in each layer. And in the case where the number of components is large, we can first remove the second layer, and we try to perform the operation in the first layer to get a good estimate. And if the number of components of this X set is small, then we can actually perform a greedy algorithm, in the second layer, to get a good estimate and to avoid the loss, in the first layer. Okay, so this is pretty abstract, but I mean we're running out of time, so let me just stop here. Okay.
maybe I could ask this question. So you have a hypothesis, which is that the Boltzmann equation solution exists.
Yes.
Where does that? Can you say something about where that fits into your proof? Where you're using that in your proof?
Okay, so here is because remember we have this factorized part. We have this non-factorized part, which is cumulant, which is the main thing, but we also have this factorized part. These factorized parts, they have to be approximate solution to Boltzmann. So basically what we know is that if the Boltzmann solution exists, then with the suitable derivations, we can construct these approximate solutions to Boltzmann, and then they behave nicely.
No, everything is non-negative.
Everything is okay. So the EH, we don't prove EH can be negative. I mean, the G is really close to Boltzmann solution. The Boltzmann solution is positive. The G, I'm not 100% sure it's always positive. I mean, because there is also this error term. So we are not really using much of positivity.
Questions?
Can I ask, sorry, I waited till the end because I'm not a mathematician. I was just wondering why you need alpha goes to infinity limit for hydrodynamics, and again, I might have missed the proof, but do you use it somewhere?
Yeah, this. Yeah, I did not talk about hydrodynamic limit, but this corresponds to basically you have this. So.
Or like, why do you need alpha goes to infinity?
Yeah, so let me show you. Basically, the Boltzmann equation is like this: dt plus f equals alpha times this Boltzmann collision kernel.
Yes.
Okay. So then, in the limit alpha goes to infinity, you are kind of converging formally. If you let alpha goes to infinity, then this guy will go to 0. This will be 0, and then those functions where BFF vanishes is formally precisely this Maxwellian. So basically, in the limit of alpha goes to infinity, your function is kind of getting close to Maxwellian. And remember, this Maxwellian is what is described, by these parameters of the fluid field. Okay, so this is why you take alpha goes to infinity.
Okay, I see.
More questions?